Okay, perfect. Well, thank you everyone for joining. Thanks for joining our online presentation. My name is Leonoor, and today I'm going to be presenting on behalf of the team I form with Barbara and Padmaja. So as you all know, the main objective of this Women in Data Science Datathon was to accurately classify intensive care unit patients as diabetic or non-diabetic, given some medical measurements that were taken during the first 24 hours of their stay at the ICU. So when we're doing Kaggle competitions, the measure used to quantify, classify predictive performance is the AUC, the area under the ROC curve. However, my team is very well aware that fairness and bias are crucial for the successful deployment of a machine learning framework in a medical pipeline, like for example, a hospital. And in order to do this, we need to have a very good understanding of the decision-making process of our classifier and determine which features have the most influence on whether or not someone is diabetic, which features increase the likelihood of being diabetic, and which features decrease the likelihood of being diabetic. It's also important to ensure that the classifier is not prone to bias and that it doesn't discriminate against a certain ethnic group or gender. So I'm going to tell you a little bit about the data pre-processing that we did during the past few days, because it was a big part of the effort we put in. So we have an imbalanced data set, which is to say that 22% of our patients are diabetic and the rest are not. We addressed this by oversampling the diabetic class and undersampling the non-diabetic class. We also removed all the features that had more than 70% missing values. And we observed that the invasive vital measurements had a lot of missing values, and so did the vital measurements taken during the first hour in the ICU. So those features were also dropped. Regarding numeric features, we did missing value imputation using the k-nearest neighbor method. So that's an unsupervised machine learning method. It's a clustering method. And we added some features, namely the range and the mean of the vital measurements. Range, for example, is very important because we know that diabetic patients struggle to manage their glucose levels, and therefore we're going to observe a large range of different glucose measurements. We also performed one-hot encoding of the categorical features, namely gender and ethnicity. And in order to be as inclusive as possible, we have an other category. So in the case of ethnicity, that is everyone who might be mixed ethnicity. In the case of gender, that is anyone who identifies as neither female nor male. And in accordance with standard data science protocol, we split our data set between a training and a testing set to properly evaluate its performance. Our choice of model was the extreme gradient boosting model, the XGBoost model. This is an ensemble of regression trees that performs classification by additive logistic regression. It achieved a AUC score as measured on Kaggle of 0.8448. And we performed a fairness check, as I mentioned, in order to make sure that we have indeed very similar predictive performance across genders and ethnicities. Finally, this is the question of interpretability is a very important question to us. So we use the state-of-the-art explainable AI framework called SHAP. SHAP stands for Shapley Additive Explanations. It's a framework based on cooperative game theory that's been adapted for supervised machine learning. So what you're looking at over here, this complicated plot, we're going to start with the left column over here. So this left column from top to bottom shows you which features have the most influence on whether or not a patient is diabetic. So the first feature, the most important one, is D1 glucose max. Makes sense. Diabetic patients have a high level of glucose. Then comes the range. So range did turn out to be important. We also included range because we wanted to make sure that we had both type 1 and type 2 diabetic patients. We know that type 2 diabetic patients often have high levels of glucose, but type 1 patients will also have sometimes very low levels of glucose. So we wanted to take that into account. The third feature is the BMI category. So this is whether someone is underweight, has a healthy weight, overweight, or obese, and then age, etc. So what I'm now going to focus on is this middle part of the plot over here. So we're going to look at the first row, D1 glucose max. This first row, every dot represents a patient. So it represents the maximum glucose measurement of one patient, every dot. The dots are red when the maximum glucose levels are high, and the dots are blue where the maximum glucose levels are low. So we see over here, this line gives you the SHAP score. So that's the importance score. If the SHAP score is positive on this side, it means increase in likelihood of being diabetic. So I read this as high glucose, high maximum glucose, high likelihood of being diabetic, low maximum glucose, low likelihood of being diabetic. Over here, if I go to BMI CAT as well, I can see that indeed obesity and overweight increases likelihood of being diabetic, and being underweight or normal weight decreases. And with age, same thing. So these types of visualizations are very useful because they give you not only an idea of which features have the most influence on the outcome, but they also give you more refined insight on, for example, what the distributions are of the importance scores. So this is the last plot I'd like to show you. This is also from SHAP. Here we're just double checking that our model does not make any silly mistakes. So we know that patients who are using a mechanical ventilator have higher glucose levels. That's in the medical literature. However, they don't necessarily have a higher glucose level because they're diabetic. So what we see over here is that the maximum glucose levels increases the likelihood of being diabetic in this region here. And yet the likelihood of being diabetic as measured by the vertical graph is lower for the blue patients who are not on a mechanical ventilator. Sorry, higher for the blue patients who are on a mechanical, so the red patients are on a mechanical ventilator and the blue patients are not. And indeed, our model knows that being on a mechanical ventilator itself increases glucose levels, and therefore the importance scores in this red area are lower. So our model is not being duped, is not simply saying that high glucose means high chance of being diabetic, because it knows that if the glucose is high and the patient is on a mechanical ventilator, some of the high glucose is caused by the fact that he's on a mechanical ventilator. So that was it for my presentation. Feel free to ask questions. I had to go a little bit faster through those last slides about interpretability, but I'm happy to talk some more. So thank you very much.
Thank you.